Hi, everyone, and thanks for tuning in. So I'll be talking about DarkSide-LowMass and our future plans to search for dark matter below 10 GeV with the ultimate goal of reaching the solar neutrino floor. So I'll start by describing the current state of the search and what exactly it is that we're looking for. And then I'll describe some of the lessons that we've learned from DarkSide 50 and how we'll apply these lessons and technological improvements that have been since then to design a detector that is designed for a low mass dark matter search specifically. I'll then show you some sensitivity projections of what we might achieve with such a detector. So to start, here is the current state of excluded dark matter parameter space for WIMPs. You can see that current experiments have paved the way for our future plans. And in particular, at high masses, there is a solid course of action being planned to search for dark matter down to the atmospheric neutrino floor, which will ultimately culminate in the Darwin and Argon experiments. The Global Argon Dark Matter Collaboration is also planning DarkSide 20K. For more details on this, please see the talk by Dr. Amelia Pantic. Below 10 GeV, we're planning to build the DarkSide-LowMass experiment, which will probe down to the solar neutrino floor. And this is looking for particular low energy signals that are about on the scale of the ionization energy of the Argon target. So the idea behind an Argon TPC is that a particle scatters on an argon nucleus, and some of the energy that's deposited is converted into scintillation photons, while some of the other energy is converted into ionization electrons. Now, these primary scintillation photons are produced very quickly and manifest as the S1 pulse, and we detect about 20% of these photons that are produced, while the electrons will drift in the electric field in the TPC until they reach a gas pocket at the top of the detector, where a stronger electric field will amplify them into a much larger signal. So due to this amplification, we can detect nearly all of the extracted electrons, and they're well above the photoelectric noise, which means that we can detect them with very high efficiency and therefore achieve low energy thresholds. However, when we go below the range at which we see S1 pulses, we lose the ability to separate electronic and nuclear recoils based on the S1 pulse shape, and we also lose the ability to reconstruct the vertical position of the event. And this is illustrated in what DarkSide 50 saw here, where we see that below 7 keV nuclear recoil energy, we start to lose the S1 pulses and we fall into the S2 only regime. However, by doing an S2 only analysis, DarkSide 50 was able to perform very sensitive searches to low mass WIMPs scattering on nuclei and sub-GeV dark matter coupling to electrons. However, for these nuclear scatters, there's an additional complication that arises below 2 GeV WIMP masses due to significant uncertainties in the response of liquid argon to low energy nuclear recoils. I'll discuss this more a bit later, but I'll say for now that we're planning a set of future calibration measurements to help address these questions so we don't have to wonder about them in the future. So this is the background spectrum that DarkSide 50 saw. Most of the energy range here is dominated by these electromagnetic backgrounds caused by gamma rays, which come from the photomultiplier tubes or from the cryostat, or from beta decays within the argon itself. And these are primarily from argon 39 or krypton 85. So DarkSide 50 used underground argon, which is very isotopically pure compared to atmospheric argon, but there's still some of these radioactive elements in it. Our lowest energy ranges are dominated by spurious electron background, which are an anomalous signal that we see that drops off very quickly with the number of electrons. These appear to be correlated very strongly in both time and XY position with preceding events, and the rate is proportional to the total event rate in the detector. So these features and other things give us the leading theory that these are due to drifting electrons interacting with chemical impurities in the argon. However, since they're hard to model ex situ, we'll mostly treat them as imposing an energy threshold on the analysis as DarkSide 50 did. So in other words, we'll start our analysis at the energy where these become small compared to the other backgrounds. So how do we reach the solar neutrino floor? So the idea is to build a dedicated detector where we particularly focus on reducing the gamma and beta backgrounds to rates that are small compared to what we saw in DarkSide 50, and ideally comparable in rate to solar neutrinos. We also need to improve the chemical purity of the argon that we use and optimize the electric field to minimize our spurious electrons and maximize our S2 signal. And so these are the design goals of the DarkSide-LowMass project. And here you can see a conceptual sketch of what we're thinking about. So we have a 1.5 ton active volume of argon that we will fiducialize in the horizontal plane down to about 1 ton. And this is contained in an ultra pure acrylic vessel, and it'll be viewed from the top and bottom by 2 arrays of photodetector modules composed of silicon photomultipliers. And this will all be contained in a large stainless steel cryostat within a water tank. So the plan is to use underground argon for everything. And DarkSide-50 measured this to be depleted by a factor of at least 1400 relative to atmospheric argon, possibly even lower after accounting for potential improvements in the underground argon extraction facilities. And so in order to decrease our backgrounds, we will focus on ways of mitigating the gamma and beta backgrounds, and also we will lower energy threshold by trying to look for ways of suppressing the spurious electron backgrounds and maximizing our ionization signal. So starting with the gamma backgrounds, there are 2 main interventions that we use for decreasing the rate. The first is using materials that have particularly been selected due to their low concentration of gamma-emitting radio impurities. A lot of this comes from the use of our low background silicon photomultipliers, which were developed by the Global Argon Dark Matter Collaboration. We're also planning to put wavelength shifter inside of the buffer region between the PDMs and the acrylic vessel. That way it can function as a veto. We can see scintillation light of gammas as they're traveling from the PDMs into the TPC. Similarly, by putting PDMs and wavelength shifter inside the cryostat, we're able to veto gammas coming from the cryostat before they reach the TPC. And so both of these vetoes are going to dramatically reduce the gamma ray backgrounds from our 2 dominant sources. The next step is to decrease the beta backgrounds. So as I mentioned, we're using underground argon, which we know is heavily depleted relative to atmospheric argon and maybe even lower due to improvements in the extraction. To further decrease the argon-39 content and completely remove the krypton-85 from our argon, we'll use the ARIA cryogenic distillation column that's being built in Sardinia. This is a 350 meter tall cryogenic distillation column, and the idea is that underground argon extracted from the Urania plant in Cortez, Colorado, will be sent to Sardinia, where it's expected to be depleted by a factor of 10 with a throughput around 8 kilograms per day. The argon will be sent to the detector, and some fraction will also go to the DART facility being deployed in Ken Frank Laboratory in Spain to assay and test the argon as it's being produced. So for more information about this, check out the talk by Dr. Vicente Pizzuto. And finally, in order to decrease the spurious electron backgrounds and maximize our ionization signal, we expect to get a lot out of having initially extremely pure argon due to the strong purification we'll get out of the ARIA column. We're also designing an in-situ purification and recirculation system. That way impurities that leach into the argon during operation can be removed. And we have active R&D going on to better understand these spurious electron backgrounds and their relationship with various chemical impurities so we can target their removal and optimize the field configuration to give us the strongest signal that we can over our backgrounds. Based on DarkSide-50 data, you can see the nuclear and electronic recoil models that predict the number of electrons produced as a function of energy deposited in the detector. This is from combining data taken by DarkSide-50 with ex situ measurements. And you can see the studies done here in the paper cited below. And using this model of the argon response, we're able to predict the signal that we'll see in our detector. And so you can see this gray curve here shows the best fit background model from DarkSide-50, showing the gamma rays and beta emitters. And you can see that our expected background rate, based on the improvements I previously mentioned, bring us far below here, down to a rate comparable with these solar neutrino backgrounds. What's not shown in this plot are the spurious electron backgrounds that I mentioned. And so these are expected to impose a low energy threshold on our analysis, and they're difficult to predict what they'll be ex situ. Though based on our current understanding, they appear to be proportional to the total event rate. And so we expect to get a significant reduction by having a lower event rate in our detector overall. So DarkSide-50 use a 4 electron threshold. And Due to the proportional decrease of beta and gammas, we might be able to achieve something similar. We will consider a 4-electron threshold as a case study, as well as a 2-electron threshold, which would require 5 orders of magnitude reduction in the spurious electron background rate. However, as I mentioned, we'll get some of this just by virtue of the fact that we're decreasing the overall event rate in our detector. And we also have active R&D going into figuring out how to reduce these as much as possible to do even better. So here you can see how our sensitivity at 5 GeV varies as a function of the argon-39 concentration in the detector. So this is holding the neutrino and gamma background rates constant. And you can see that we get significant sensitivity out of the argon-39 reduction that you see here. And given the throughput expected from ARIA, we expect to be able to adequately purify 1.5 tons of argon in a reasonable time scale. However, we also find that there's not really much to gain by going larger. Higher exposures don't really improve our sensitivity, and this is because we're approaching the neutrino floor and we're already so close to that. So larger masses will be harder to isotopically purify and they don't gain as much. So this gives us a strong motivation for staying around the 1-ton fiducial mass plan. So here you can see that we are close to the neutrino floor already. These two plots demonstrate what we could get with a 2-electron or 4-electron threshold. And these bands represent the uncertainty that we have in our quenching model. So the dominant uncertainty in the quenching model that is not being profiled over and therefore represented in this band is the way that the fluctuations in the number of electrons produced varies as a function of energy. So in particular, we can assume that there's no quenching fluctuations and the number of electrons produced is given by the quenching factor, the mean quenching factor predicted by the model. Or we can assume that there are binomial fluctuations around that mean. And you can see the two extremes that we get here with more conservative results predicted by the no quenching fluctuations model. And you can see that there is a big difference here. And so we're planning calibration measurements to explore what actually is the appropriate model to be using here. And this mostly models below matters below 2 GeV WIMP masses. You can also see that there's very significant dependence on our sensitivity on the threshold that we use and on the total argon-39 background rate we have. So the dark blue curve here shows the background in the case where we only have 7s backgrounds, whereas the blue curves assume that a constant gamma ray background rate and either a factor of 10 or 100 argon-39 reduction relative to DarkSide-50. And you can see that both of these are important factors. And finally, you can see how we measure up against other planned experiments and our ability to reach the neutrino floor at a tonne-year exposure. So we expect to have a very exciting physics reach, and it will be very complementary to the other experiments that will be probing a similar region of parameter space. So keep your eyes peeled for our upcoming paper with sensitivity projections and more details on the studies that I presented here. One of the key hallmarks of this plan is that we're getting substantial gamma ray background reduction due to the low gamma materials that we're using and our twofold veto system. The biggest room for additionally improving our sensitivity comes from further reducing the argon-39 content and by lowering our energy threshold, which will largely be a matter of how low we can get our spurious electron background rates. So we have ongoing R&D exploring this question precisely, trying to figure out the best way to suppress the spurious electrons. We're also planning low energy coil calibration measurements and finding ways to further reduce our energy threshold. We're doing this both through R&D and through studies of DarkSide-50 data. And so you can see one paper that we've recently posted to the archive and another one that will be coming up soon, exploring exactly this. Beyond our potential sensitivity to dark matter, we also expect to have some sensitivity to supernova burst neutrinos. And you can see the paper cited below, exploring the sensitivity of a low threshold argon dark matter search to core collapse supernovae, particularly focusing on the DarkSide-20K and Argo experiments. So thank you for your time. And if you have any questions, feel free to ask me. Thank you.